What's up, guys? We're going to do this physics question. Question number 2. I'm your physics tutor. I'm struggling in physics too. The question is, an 80-kilogram mail bag hangs by a vertical rope 3.9 meters long. So we know that the length is 3.9 meters. And the mass of the bag is 80 kilograms. And the postal worker displaces the bag to a position 2.1 meters sideways from its original position. So if we just want to draw this was the bag initially with the length L, and it did weigh the mass B, and we got a worker displacing that, so now it looks something like this. Now we could do a dashed line here to indicate the change in the displacement, and horizontally 2.1 meters in displacement, and the L is still the same here. And the rope is taut, meaning, that's a little word for you, taut just means not slacked, meaning it's tight. Alrighty, so what you want to do here is identify your theta. And it's convenient to identify your theta right here, because we have the length L and our displacement. So what you want to do is identify here, we have L being the hypotenuse of this little triangle we've made, and D being the opposite. So what is that? That's sine theta. Opposite over hypotenuse, guys. So by that, we could do sine theta is equal to 2.1 being the opposite over 3.9 the hypotenuse. Rearrange it so that theta is equal to the arc sine, or the inverse of sine, or whatever. 2.1 over 3.9. And that's our theta. And this is important. We'll find that out later on. Anyways, the actual question that we're solving for here. I probably should have said that first. What horizontal force is necessary to hold the bag in the new position? So we're solving for horizontal force here. So this is going to be Fx. It'd be useful to draw a free body diagram of this box right here. So let's just draw it. We have the weight, mg. There's no normal force here, but we do have tension, and we could decompose the tension, sorry about that, tension diagonally. We could decompose it into its x and y's components, ty, tx, and then we have that force keeping it horizontal too. We're going to just put it as F. And ty, you could imagine it right here. Ty is like this, so we're solving for this length right here. It's equivalent to that, and that'd be basically t cosine theta. T cosine theta is equal to ty, and then t sine theta is equal to tx, because it's opposite right here. Hold on, maybe a different color here. Opposite right here. That's basically correspondent to this right here. Anyways, we got 4 forces acting on it right now. You could ignore this one since we decompose it. Sorry about that. And now we can just add the forces together. First in the y direction. And since the y direction doesn't move, we could just do ty minus mg. So we get ty is equal to mg. Now for our horizontal, we're going to do the force minus t of x, meaning the force is equal to t of x. Now we could sub in the values we found for ty and t of x to each of them. So t of y is equal to t cosine theta equal to mg. And then t of x is equal to t sine theta. Alrighty. So what you want to do here, guys, we have these new equations. F is equal to t sine theta for the x direction. And then for the y direction, t cosine theta is equal to mg. You want to isolate the tension. F divided by sine theta is equal to tension. So now you have tension independently as an independent variable. And for this one, you want to divide it by cosine to get t by itself, to get mg divided by cosine. And set them equal to each other. Since t is t, that kind of just makes sense. So F divided by sine Sorry guys, hold on. So F divided by sine. Make that equal to mg cosine. And then solve for F. So just multiply sine theta. So now you got sine theta over cosine theta, and that's just tangent. So really, this is what you're left with, mg tangent theta, and we solved the theta earlier right here. So you just want to plug this into the calculator with what you know already. So the mass of this is 80 kilograms. Gravity, 9.8, and then tangent theta is the arc sine of 2.1 divided by 3.9. And you want to put that into your calculator, and that should be your answer. Let me put that into my calculator really quick. You're going to get, first I'm going to solve for arc sine really quickly. Arc sine of 2.1 divided by 3.9. You get 32.57. Now you're going to get 80 kilograms multiplied by the force of gravity, 9.8. That's the acceleration's gravity, my bad. Tangent, 32.57. And your answer should be approximately 501 newtons. And that is the answer for horizontal force to maintain this little box in that displaced position. What's up, guys? This is your physics tutor, and this is part B to the last question. This question is, as the bag is moved to this position, how much work is done by the rope? Now, we're calculating work done by the rope. Now, let's just draw this picture again. This is what we have right now. And then we have the force acting this way. Does this look familiar? You're dang right. This is a 90-degree angle. And what do we say about 90-degree angles? They're perpendicular. And what does work and perpendicular come to mind? If two work vectors or two vectors erase are perpendicular, then there is no work done. Meaning work by the rope, since it's perpendicular to the displacement. I'm trying to write it, but you know what I mean. Work is equal to 0 because these two are perpendicular. That's the rule, guys. Remember that. Alrighty, guys, this is part C. Very similar to the last part. As the bag is moved to this position, how much work is done by the worker? Now, since this box is at rest, the work is equal to 0, guys. Keep that in mind. Now, let's use one of our major equations. Let me just pull it up right here. Our master equation, we're going to use the general relationship for kinetic energy and potential energy, which is the initial kinetic and initial potential energies plus work others is equal to the kinetic final plus potential final. Now we have no kinetic and we have no that, so that cancels out, and we're solving for work by the worker. So what you got to do is just move your things here. U2 minus U1. That's final minus initial. Does that ring any bells, guys? Yeah, you're right. That is delta U. In other words, this is mg y2 minus y1, because that is potential energy. Oh, and this is potential energy. We're talking about gravitational potential energy. It's only two types. In this case, this is gravitational potential energy because of the gravity here. There's no spring here for it to be elastic or springy, you know what I'm saying? So we're dealing with gravitational potential energy, which is mgy. So the delta change would be mg parentheses y2 minus y1. You could even just write it out, but okay, fine, I'll write it out. Mg y2 minus mg y1. You could kind of see how that you could just factor out the mg to get this equation. And from here, you just got to plug in your numbers, guys. So we got 80 kilograms, 9.8. And then the change, we could calculate that over here. I kind of did it already before. Actually, I just start over. I think it's quite a bit. Oh, it's down there. Oh, whatever. I'll just do it again. So what you got? You got a theta. We got a box here. We got 3.9 here, and the displacement, I believe, was 2.1 meters. They're all meters. So basically, we got to solve the change in the y from where it was, like right here, to where it is right there. So what we need is to find this thing right here, the y. How do you do that, guys? It's Pythagorean theorem. 2.1 squared plus b squared is equal to 3.9 squared. You do that, b is equal to 3.9 squared minus 2.1 squared, all square rooted. Now what you're going to do, actually, I'm just going to put that in my calculator. I think I still have it here. Yeah, that should be 10.8. Oh, I lied. 10.8 square rooted. Take the square root of that, you're going to get 3.286, around there. Alrighty, that is our original y value. That is our missing value right here. And this new triangle. Now what you're going to do is take the original, because remember, it did start off right here with 3.9. That was the initial y. That's what this guy is right here. And now it kind of decreased going this way. So what you're going to do is just subtract the original one, 3.9, with this one, the one we just solved with the new one, which is 3.286. Plug that into the calculator, and you're left with 0.613666. So I guess that's like rounded 6.14. 614, sorry, 0.614, sorry. And that is the delta y. We just subtracted the final and the initial. Or the initial and the final. It's the same number. Anyways, after you have delta y, you just plug in the value to what we were going to do right over here. 0.614. And your answer probably would be 481. Now, since this is work, this is going to be joules, and that should be your final answer. Or around 480. That also works too.